in that diagram, is there one single melting point? Okay, it depends on the composition. Yes, and in fact, the main thing what a phase diagram shows us is which phases that exist at a certain temperature and now I say X for the composition, yeah? And then we go here to some point and then we know it is liquid. Here we know it is liquid plus lead. Here is the eutectic point. Here we have liquid plus lead plus tin. And the melting point is more or less just the transition between these. In fact, your proposal was also correct insofar as a phase diagram is normally not made by just going to one temperature and composition, but rather by finding out what are the transition points or lines. Yes. So we cool, for instance, a certain composition and look. We have two. What is it? Line is not steady, for instance, when you cool it, the temperature line, and then that would be when we cool here. Yeah, it would be in 3 places, here, 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 and then we do it here, and then we see these, and in that way, going down here, we have that point and that, and yeah, here I forget one, and by connecting these, we get the line. Yeah, just it's some cooling or heating experiments. And in that way, a phase diagram is constructed. The phase diagram gives us the information, and in that way, when we go to a certain composition, we can expect which phases are there. For instance, when we go in here, we have tin plus lead. Or when we go here, we are on the tin-rich side. We see when we have a composition like here, we see we have tin plus silver 3 tin. Yeah, and so we can expect, going to that image, that is probably silver 3 tin. So in that way, before doing a microanalysis, we just go into the diagrams, and at least for binary systems, we can have an estimation what is there. For ternary systems, it's already more complex, but in the end, we can derive that information from the binary diagrams mostly. So in that way, and here we can say, if we are on the tin side, rich side of the phase diagram, so we typically have copper 6, tin 5, but we can also, as we have on the other side still copper, we can also expect that it is copper 3, tin here. So, and in that way, we can at least have a guess what will be to be expected. On the other hand, on On the other hand, it is better to make a microanalysis, but you have to pay typically 200 euro per hour of using such an instrument. And so such analysis is always quite expensive. Yeah. So here is, that was another PhD work. When you want to look at reliability of such die attachments, you can have, we know there are fatigue problems. So fatigue means mechanical degradation, we get cracks, and finally the chip falls off or the chip is overheated due to the cracks. But there is one thing which is important in solder alloys. Also, the internal structure of a solder alloy is not stable over the operation time. That is contrary to all materials we have in technology for construction or for structural applications. So you're sitting on a chair made of steel tube, and that steel tube will not change. If it doesn't corrode, it's still the same steel. When you would cut it and look like a microsection, it's always the same steel. It's the same with the engine of your car, or with the copper winding in an electrical motor, or with the wing of an aircraft. Yes, I wouldn't, let's say, yeah, I wouldn't like it if I would know the structure of that changes during the operation time, because when the structure changes, the properties will change. On the other hand, it's different in solder material. Solder material always changes. The main reason is that the application temperature of solder materials is high related to the melting point. So solder material is always operated in a high temperature range. That means high temperature is not how high is the temperature really, but it's a relatively high temperature. And here the reference value is the melting point. And typically solders are operated above 50% of melting point, and that's high. And so we can see initially we have here the tin structure, that's a white thing. Then we have here something looking eutectic of silver-3 tin dispersed in tin. That's these gray areas. Here we see the small dots. What we can also see here, these longer structure, that is copper tin intermetallics, and that's a new solder material. Now, when we operate it for 2000 cycles or for many hours at high temperature, we can see the structure completely changes. The copper tin faces, they grow, yeah. So, and we also see the silver-3 tin makes bigger particles. So generally the structure changes, and having cycles gives us more structural change than just constant high temperature. So that's, cycling is more the reality. And so we can see it does lots of change. And of course, the solder must still work and be strong enough after such changes of microstructure. Another thing that is important is we have an intermetallic layer here, and that layer is growing especially at high temperatures. And when that layer is thick enough, you can see that black line here. What is it? The black line? it's a crack, yes. And that's the reason is such intermetallic phases are brittle and they do not tolerate stress concentrations very much. And so a crack was formed. And that's also a result of aging of solder joints. On the interfaces, cracks can be formed. You had a question. Yeah, it was in that case, it was, I have to look, -40 to 150 degrees centigrade, for instance. And we heat it and we cool it 2000 times. And yeah, so we go 2000 times to high temperature and we cool it. The effect is that in such a material, we always dissolve something of the silver and the copper in the tin at high temperature, and then we release it or we precipitate it again at lower temperature. And that dissolving, precipitating, that increases such degradation processes significantly. And that's a cycling. So cycling in automotive electronics is a much more important test than just keeping it at high temperature. One of the main reasons we have also constant high temperature test is that when we do temperature cycling, we always have two phenomena. One is from the cycling itself, and the second is from the time it is at high temperature. And we want to distinguish that. And in that way, we make additional just high temperature tests and look what happens there, what happens in that combined test. And now what is just a temperature effect and what is a temperature change or temperature cycle effect. That's one of the reasons we do high temperature continuous operation, but the cycling is a relevant test. Yeah. And again, that was a master thesis at that time. That student, he did his work in our Chinese lab and in Shanghai. And again, it was these TO220 we had. We can see that's the interface to the device after just after the soldering. And here we can clearly see the two intermetallic phases. To the copper side, copper-3 tin, that's a thinner layer. And here it's a thicker layer of copper-6 SN5. Here that looks still fine. Here we do not have yet cracks. And what we also find out that the growth of that layer is not linear with time, but it is growing with square root of time. But of course, growth speed also increases with temperature in an exponential way due to Arrhenius equation. And so we did that investigation for both of the phases, but we could find out that after, for instance, 1,600 hours, cycles, the thickness of that intermetallic totally was 6 micrometers. And that's already quite high, we must say. That's one of the limits of soldered joints with tin, that we have such a growth of the intermetallic phases, and when it's too thick, it will crack. So, okay, in that case, I must say it was not 150, it was 125, but in all later projects, we went to 150 degrees centigrade. Okay. I would say we're finished now. What we can what we can also see is that there are different solders. We will see them next time. For instance, when we have an indium tin solder, it can solder at 143 degrees centigrade. I presently have a project where we have made a solder consisting roughly 50-50 of indium and tin. And here we can solder down to 118 degrees centigrade. The trick is that later on we make a certain heat treatment, and then the melting point can go up to 400 degrees centigrade. So that's one of our projects. But in the next time, we'll see more about solder alloys we can use here. Okay, that was for soldering, more for metallurgy. Next time, we will also see real processes for die attachment or for surface mount technology, which are based on soldering, which is the most important interconnecting process for devices on a substrate. Okay, thanks for your attention.